Have you ever wondered why video game physics sometimes lose their minds? Cars clipping through walls or characters rocketing into the stratosphere, it all comes down to how computers simulate time. In reality, time flows continuously, but a game engine can't calculate infinity. It has to slice time into tiny, discrete chunks called delta time. The absolute simplest way to calculate the next position is forward Euler. You take where you are right now, look at your current velocity, and blindly jump forward by one time step. The problem? It constantly overshoots. By projecting blindly along a straight tangent line, forward Euler literally invents artificial energy out of nowhere. Do this for a few seconds and your orbit completely explodes. To fix this, mathematicians look into the future using implicit or backward Euler. It calculates your next position using your next velocity. But because you don't know the future velocity yet, it requires solving a heavy system of algebraic equations every single frame. Worse, instead of creating energy, it aggressively destroys it, acting like a cosmic brake pedal that collapses your simulation. So forward Euler blows up your world and backward Euler freezes it solid. Neither works for real-time games. A solution to the shortcomings of the Euler method is the symplectic or semi-implicit Euler method. By simply updating the velocity first and feeding that brand new velocity directly into the position calculation, the energy errors perfectly cancel each other out. It's incredibly cheap to compute, yet perfectly stable forever. It's the hidden engine driving almost every 2D physics system today. But what about cloth, ropes, or ragdolls? For that, we throw out velocity entirely and use position Verlet. It derives motion purely by comparing where a particle is now to where it was in the previous frame. Because there is no velocity variable to break, you can instantly smash objects into hard boundaries and resolve constraints perfectly. While position Verlet looks backward at history to jump forward, velocity Verlet syncs position and velocity in real time using look-ahead acceleration, preserving perfect orbital energy for complex forces. If you are building a flight simulator or NASA orbital mechanics, you trade speed for raw precision using RK4. It samples 4 different look-ahead points across a single time step to plot a hyper-accurate trajectory. To optimize it, advanced engines use adaptive time stepping, taking massive time jumps when things are moving straight, and slowing down to calculate microsteps the microsecond a sharp collision happens. In conclusion, different types of integrators are useful for different scenarios. Here's a matrix that clearly displays key differences. At Sleepy Sunrise, we use various integrators to simulate real-world phenomena in cosmological settings. In the end, however, we find that stability is everything.